And we will now go forward to the next talk from Professor Philipp Thies. Professor Philipp, are you available?
Yeah, I can hear you well. Can you hear me?
Yes.
Hey,
Professor
I'll try and share my screen.
Good morning. He is a professor of renewable energy, offshore reliability, and deputy head of engineering at the University of Exeter, UK. His work aligns with computational modeling with application-driven design and reliability improvements, focusing on dynamic power cables and moorings for offshore energy. He is a co-director of EPSRC Supergen ORE Impact Hub and has led multiple mooring demonstration and dynamic submarine cable test projects. His work on dynamic submarine cables has received the IMechE Best Paper Award. Philipp is also a member of the UK's Health and Safety Executives Science, Quality and Assurance Group, SQAG. Over to you, Professor Philipp.
Kind introduction. That is a lot of words for saying I work on offshore renewables, and in particular on risk and reliability. So a lot of the work I've done can, I think, translates over to green hydrogen. And it's an emerging field for offshore wind, because I think we're now at a scale where we're actually looking to what do we do with all the electricity if the plans are forthcoming. This is what I've tried earlier in the week. So the way was mapped out all the way to India. Everything was booked. I only made it as far as London, which is still a good 5-hour drive. And then they pulled me off the plane. So apologies I can't be there in person. I will definitely try next time indeed. So for offshore wind, at the moment, kind of conventionally, there's a lot of infrastructure that'll have to be offshore, and indeed is already offshore. So what is commercially built? See if I get my my pen. What is commercially built at the moment are kind of fixed offshore wind. We've got just shy of 13 gigawatts in the UK now, much more globally. And the infrastructure here is really a piled foundation and then a cable, which are called inter-array cables, that lead to the fixed offshore substation, or if it's closer to shore, an onshore substation. And it's that electrical infrastructure that allows you to kind of export the electricity. What we're having now is, because we've built around the coast, we've built all the offshore wind farms that we could in relatively close proximity. And we're now moving much further offshore. So some of the Dogger Bank projects that people may have heard about, they are up to 100 kilometers offshore. So the cost of that electrical infrastructure increases, and people start to think about, well, that's one reason people start to think about hydrogen production offshore. The second reason is that in many ways, the kind of installation of offshore wind turbines is quicker and at faster pace than the grid infrastructure on land. So some of the projects cannot be connected, or will have struggled to connect if the grid isn't reinforced in time. And you can see kind of with what is planned now, and there's a few pilot projects out there on floating wind, the kind of electrical infrastructure in terms of the cables, the dynamic cables, and that's a lot of the work I do, is much more exposed. So there's a number of good reasons why hydrogen might be considered for offshore wind. We've heard a lot about green hydrogen. What is it with the color? Just conscious that not everyone works in this space. So hydrogen by itself obviously hasn't got a color. The community invented a couple of colors to distinguish basically how is it produced. So when we talk about green hydrogen, what we mean is we use renewable electricity to conduct electrolysis to then generate the hydrogen. So that's important. So I'm talking about offshore wind, but you might as well use, for example, solar energy. There's two main kind of electrolysis mechanisms. One is the alkaline electrolysis, and the other one is the proton exchange membrane electrolysis. And I'm highlighting that here because it's important to kind of look at those and then ask the question, how are they actually applicable? How are they suited for what is likely to be offshore? So at the moment, kind of the larger commercial application really is in the alkaline electrolysis, largely because it's cheaper. You can exchange the electrolyte. It runs best when you have a steady electricity supply, and it kind of loses performance and efficiency, and indeed you compromise its lifetime if you start switching it on and off, or if you kind of vary the load you run it under. So it's not really well suited for fluctuating load supply, which is what you have offshore, unless you have a buffer, because you've got times when the wind blows and you have a lot of electricity provided, and times where you may have way too much. So unless you have a buffer, you cannot directly apply the alkaline electrolysis, or not as well. Whereas you look at the proton exchange membrane, you have a solid polymer barrier, and kind of the properties here, it operates at higher current, and it can handle kind of load performances when the load fluctuates. So it's much better under partial loads. So from what system would we prefer offshore, PM kind of offers benefits, but it's yet not at the kind of large scale industrial production that you'd require. So it's more small scale industrial use at the moment. So that's one challenge to go forward. Whereas we want properties that the PEM offers, it's not really there from a commercial basis yet. The other challenge that we have is, and it's, if we look at applied research, and it's always about cost as well. So this is an interesting graph here from McKinsey, where they try to map out kind of the global production costs for hydrogen, and green hydrogen in effect is in competition with kind of the other colors, blue and gray in this case, and they reckon round about the 2030s, there's a crossover when we have enough renewable, or when the cost comes down enough for green hydrogen to kind of beat both blue and gray hydrogen to it, and be more cost effective. And that's important because the industrial or the commercial application will only be forthcoming if the business case really stacks up. And I'm bringing this slide here because I'll have a slide at the end that kind of shows projections. So for hydrogen in general, it's some way in the future, and this is one of the reasons. So at the moment, it would be more expensive than other alternatives. And the reason is that you need a market. So for electricity, it's while you're there, you export electricity and you can have multiple uses. For hydrogen, it has to be more specific. So you need a definite demand case, and that's at the moment the primary use, or the pilot case studies that are coming out and are being worked with, are basically from industry. They have direct hydrogen needs, a little bit for transport, and some work around heating, but not so much. So you really need to think about those supply chains and the kind of the end usage that's required, and that's as much to do with the technology infrastructure as with policy decisions. Because for transport, for example, you have to have the infrastructure either to fuel a hydrogen economy, or you decide to go largely electric. It's unlikely that you'll have two complete infrastructures, or pick sections. So heavy vehicles, for example, trucks and buses, where you say this part of the transport sector we can fuel with hydrogen. So there's political decision making and investment required as well. So whilst we're focusing obviously on this part here, producing it offshore and getting it exported and getting hydrogen out of the electrolyzer, you need a clear view of what is the use case for it. And that's what you see in the pilot studies and kind of the commercial pilot projects that are being out there. So there's a lot of activity both in the UK and Europe. And there's different schemes. So I'll highlight a few here. So Germany started the GET H2 nucleus project, where they're producing, as you say, conventional almost offshore wind electricity, and then they export that electricity through the grid to an onshore electrolyzer, and they're conducting the electrolyzer there. You can do that when the wind farm is fairly close to shore. That's fine. And then what they have is they link it directly to some of their industrial centers that require the hydrogen, so they can pipe it straight to them. And again, distance is important here because piping it is obviously more expensive than conducting electricity. So you want close proximity of the farm and the end users. The other scheme is this one here. So that's H2Z in the Netherlands. They do two things at once. So they have a few wind turbines that have electrolyzers directly with them, and generate hydrogen on the turbine, if you like, and then export it directly. And you have a few turbines that kind of, again, conventionally generate electricity, and they have an electrolyzer offshore. And then that's either being stored or exported. And then the bottom one here, that's the Hydrogen Turbine 1, the HT1 project in the UK, where they're trying to retrofit some of the existing jacket structures, basically with an electrolyzer and the hydrogen generation system, to then have a standalone system that's able to export hydrogen. And that's of interest because you can foresee a system where you actually have those as refueling stations for vessels and the like when you're out at sea. And then another one, the Aqua Ventus in Germany. Again, they do a mix, so they have some standalone electrolyzers on the turbines and on those platforms, and then also large electrolyzers that kind of centralize the electricity and then generate hydrogen. So it's about interfaces, and it's including those, or it's considering that integration challenge really, because it's not enough to produce the hydrogen. You need to think about how do you ship it out, how do you pipe it out, where do you get your water from to actually carry out the electrolyzers, what is the treatment to do so, where do you treat your hydrogen, is that offshore, or do you all bring it onshore and treat it there? So there's a lot of infrastructure planning that has to go with it. And you can repurpose some of your gas grid if you have one, or establish a new hydrogen grid if you have to. So there's quite a few jigsaws that kind of have to be arranged correctly to make this work as a system. And they're trialing that out really through the pilot systems. One thing we do here at the university is in terms of the use and the end use of the hydrogen. Where you'll have a fuel cell to again then convert the hydrogen back into electricity. And in particular for vessels, one of the challenges there is, do you get the same duty cycle? Can those fuel cells provide the load cycles that you require at sea? So we've got this hydrogen boat center where we can simulate and test fuel cells in the lab to see are they actually fit for purpose before you take them on the vessel, because you want to test as much as you can in the lab before you actually go out, certainly at sea with it, or into commercial applications. So that's the last slide, which forecasts what the UK hydrogen economy could look like and where the hydrogen would come from. So you can see, if we're here, it is tiny at the moment. So there's no meaningful capacity. There's a few pilot projects, as I said, and where they're testing out how does it all work, how do those different pieces fit together. And then it could be, if the political framework is correct and the sector pivots towards it above and beyond electricity, there could be a potentially huge market, but you can see it's somewhat out in the future, which is fine, because I think from a research perspective, that offers us a lot of opportunity for impactful R&D. So it's thinking about those systems, it's thinking about the integration, it's thinking about the best solutions and how to demonstrate existing technologies which are available, but they need to be integrated, demonstrated, and indeed coordinated, so that we can learn from those pilot projects which are forthcoming, because they won't be perfect to begin with. We'll have to learn from them, and then work with industry to figure out what is the actual demand, what are the best and commercially viable use cases, and what's the investment that's required. So I'm very hopeful that some of the applied research that we do at Exeter actually contributes exactly to that space. And I heard my colleague there talking about producing fuel cells. If you do, you can come to us to test them, to see can they kind of produce the reliability and the load cycles that they require. So thank you very much. Contact me for any questions, both kind of research and study inquiries. We have a number of postgraduate MScs and a lot of research in clean energy engineering, spanning really everything from solar, hydrogen, offshore wind, so a range of technologies. So I'm very happy to take any questions, and I'm looking forward to be in Chennai on the next occasion.
Any questions to Professor Thies?
Hi, Saman. Yeah, I can hear you well.
Sorry, it should be all right now. I just wanted to ask you just a very quick question. Being located in UK, how would you compare the HVDC and the hydrogen transportation in terms of cost, energy security, and so on? So, because there are some kind of speaking of Australia being far from other countries, it does make sense to talk about green hydrogen all the times, but when it goes to Europe, just a kind of dilemma or chicken egg problem that I'm just asking myself is, why doesn't Europe just look at HVDC as a complement to green hydrogen, as there are kind of, this is a kind of condensed geographical location? Thank you.
Yeah, that's an excellent question. And it's exactly that competition between almost electricity and hydrogen. So I think that they're really two competing infrastructure systems. It wasn't in my presentation, but there are there's a lot of activity on HVDC. So that one of the recent ones that's been installed is the NEMO link. So they're building gigawatt capacity DC links between countries, and in particular out in the Baltic Sea, kind of in between the UK and Germany and the Benelux states. They're having vast plans of actually having islands of offshore wind, and then connecting that up all with one grid. But at the same time, they're trying to do this, or plans are there to say, can we repurpose existing, because they have a gas grid as well between Norway and the UK, for example, and mainland Europe and the UK. So that competition is still there. At the moment, I see electricity moving quicker because it is quicker, and they have the usage is a little bit easier. If there's a stage, because it comes to I think overall system efficiency as well. I mean, hydrogen, I'm in two minds about hydrogen, because I think as I said, the use case has to be defined. If we're in a situation that we have too much electricity, like literally, we'd have to curtail the offshore wind farms because the grid can't take it. We've got no good use for the electricity. Then you want to generate hydrogen. Otherwise, because if you think about the conversion chain, you're producing electricity in either case. Then you go to electrolysers, and then you go backwards. So you're losing efficiency of the overall conversion chain. So it would be things like, say, maritime transport, heavy vehicles.
Yeah. Is there any sort of concern with respect to essentially hydrogen being a little unsafe with extreme weather conditions that might arise at sea?
Yes, indeed. But there is the experience. So you've seen some of those platforms. There's the experience from offshore oil and gas. So you would have those platforms and those electrolyzers sit well above the sea level to be well out of everything. There is reliability challenges with the electrolyzers themselves. So you need to have them very sheltered and have a good system around it to kind of make sure there's no kind of salt water or any of those corrosive atmosphere coming in. So you need a really good system to protect the electrolyzer itself if you run it offshore. And I think, again, in those pilot studies, that's one of the things that will almost decide what the system setup is. If you cannot quite achieve, because the offshore engineering I've done, you always try your best, but something is always coming through. So you're going to have challenges offshore. And if these are too large, then I think people will refrain to actually going onshore and have one electrolyzer, and you could integrate that with the grid. Because we have options. You can build the grid and have electricity come in via DC, for example, over longer distances, and then just have a few large-scale centralizers or centralized electrolyzers that generate it. So I think the interesting research question is really it's an infrastructure question, as not so much a technology. It's like, what system do you want? And that's a lot to do with context and industrial centers where you want those close proximities. So people talk about the hydrogen economy, but I think it's a good way to just symbolize and kind of transmit the message that it's a systems problem and an infrastructure question that you need to answer.
Sure. So I think we will close the session at this moment and give an applause to Prof. Thies as well. Thank you very much, sir.
Thank you so much. Thank you.
And before we leave, a small memento for the session to the speakers.
Philipp, I think we should post one for you.
I'll keep it somewhere safe next time I come around.
Okay, yeah, thank you. We will close.